Hello, we are Group 7. We have chosen to go over transportation engineering as part of the EIT preparation. So let's get on ahead. So the transportation engineering portion of the exam goes over 5 different sections. Those 5 sections are geometric design, pavement system design, traffic capacity and flow theory, traffic control devices, and transportation planning. There are about 9 to 14 questions in the exam are comprised of this section. Our recommendations for this section of the exam is just to practice as many examples as possible. Make sure you know how to reference the FE reference handbook to find necessary equations. Make sure you know how to use said equations and know what variables stand for. We would also highly recommend to reference your class material from CIVI 481 and CIVI 482. A great textbook to go over as well, besides the FE reference handbook, would be The Principles of Highway Engineering and Traffic Analysis by Fred L. Mannering and Scott S. Washburn. Some resources we recommend would be, again, to go over your classwork from CIVI 481 and CIVI 482. Online, we would recommend looking for practice exams, YouTube, but be careful what sources you pull from, and online courses. Literature, the textbook we mentioned earlier called Principles of Highway Engineering and Traffic Analysis. Certain professors from SDSU are also a great resource, such as Charles Stoll, Sam Amen, and Nancy LaCourie. Organizations we would also recommend is SDSU ASE and SDSU Tri Epsilon, as they both have FE exam review sessions throughout the year. Our study plan is as follows. We would recommend studying over a period of 3 months for the traffic engineering section, study about 2 to 3 hours per week. For the transportation section, on month 1, we would recommend going over geometric design and pavement system design. Month 2, we would recommend going traffic capacity and flow theory, traffic control devices, and on month 3, we would recommend transportation planning, and also going over any other section you felt weak on. The following example will show the geometric design portion of the exam. This portion refers to design dimensions and arrangements of the visible features of a roadway, such as pavement widths, stop sight distance, horizontal alignments, vertical alignments, design of streets, highways, and intersections. Possible questions you can see on this portion of the exam are stopping sight distance, vertical curve design, horizontal curve design, and super elevation. The following example is a 2-lane rural road as a 10-degree horizontal curve extending for 750 feet along a center line. The road is 20 feet wide with 2 feet wide shoulders, and design the speed for a roadway is 50 miles per hour. So the first part of the question is to find the super elevation needed on the curve to give a side friction factor of 0 at the design speed, and also to find the spiral curve transition length. I would recommend first going to your FE reference handbook to find the following equation. E plus Fs equals V squared over 15R. Fs is your side friction factor, so we cancel that out as 0. We plug in our variables, but then we realize that we don't have R. Again, you can go back to your reference handbook and find the equation for R, which is 5729.58 divided by D, which stands for 10 degrees, getting the radius of 572.9 feet. Putting that into your previous equation will result in an E equal to 0.29 or 29%. Part 2 is solved in a similar fashion. Reference your FE reference handbook. Find the equation for LS, which is equal to 3.15 V cubed over RC. Some students might be tripped up because the question doesn't mention what C is. If you look at the handbook or just for studying, you can find that C is usually 1 feet per second cubed, unless the question states otherwise. And seeing as the question does not state, we will use C equals 1 feet second cubed. Plugging all these variables into the equation, 3.15, 50 cubed over 572.9 times 1, you get a transition curve length of 687. I will now pass the rest of this presentation to the rest of my peers. Thank you.
I'm going to be talking about pavement system design. The main objective of pavement design is to provide a structure that is able to distribute the load safely to the underlying subgrade. On the left, I have a picture, an illustration of pavement design. We have weak pavement and strong pavement, and underneath is the subgrade. It shows you how high stress is due to the poor spreading ability, and then we have lower stresses when it's strong pavement due to good spreading ability. Possible questions is the pavement load, the pavement layers needed, pavement types, and the required thickness. So this is going to be an example problem. Basically what it's asking is we have a flexible pavement to be designed by a flexible pavement a flexible pavement system is to be designed using the AASHTO structural number design method using this criteria. We have the AC, aggregate, and the subbase. Those are all given, and the coefficient of the structure layer 0.44, 0.25, 0.10, those are all given, and also the structural number 2.50, that's as well as given. So it says, if the minimum thickness of the surfacing and aggregate base are used, what is the required thickness in inches of the aggregate subbase most nearly? So on the right we have the solution to the problem. On the top you kind of have what's given, AC surfacing, aggregate base, aggregate subbase, and then we're finding we have the minimum thickness of AC surfacing D1, we have the minimum thickness of aggregate base D2, and we're given the structural number, and we're assuming that M is 1 for the drainage. Now what we're going to do is we find the thickness of the subgrade based off of this equation. We have A1 D1 plus M, and we're adding the A2 D2 to the A3 D3, and from that equation we get D3 is going to be 6.2 inches, so approximately it's going to be 6.5 is going to be the required thickness. This is how you solve this pavement system problem.
3. The passenger car flow rate can be calculated based on this equation, and it is found to be 1,601 passenger cars per hour per lane. If this is less than 1,400, speed does not equal free flow speed. So speed is calculated to be found 50.54 miles per hour. The density can then be calculated based on the passenger car flow rate over the speed, which is calculated to be 31.7. 31.7 is greater than 26, and it falls in this region right here. So this would be a level of service D. So based on the density of traffic determined, a level of service rated D is found.
Traffic control devices. This part of the exam covers the operational performance indicators that are used to characterize distinct traffic streams. Uninterrupted traffic flow is defined as that which occurs without the aid of signs, traffic control devices, and intersections. Some possible questions could regard safety, the capacity, the traffic flow, as well as the traffic control devices. For the example that I found, it's asking the design requirements, a section of the highway are, and then it gives you all of the information. And then, for example, it asks for the total stopping sight distance for this highway. And then the other question asks for the minimum length for a crest vertical curve joining the grades of plus 4%, negative 4%. And then here on the right, you can see I solved this, and they're basically just equations that you got to plug it into, and you have all the information given here. So once you learn that part, then you should be fine for that section. Thank you.
So transportation planning is the last section of the transportation section of the FE exam and involves problems including trip generation, travel forecast modeling, safety, transportation modes or choices, etc. And these are modeled through various methods such as probability distributions, crash rate models, the gravity model, and etc. So like the example we have here, this is going to consist of the gravity model, which is going to be used to compute trip generation in a location. So this example uses the gravity model and utilizes number of trips attracted, friction factors, total trips reduced from the zone in order to calculate trip generation produced from the zone.